try to discuss this problem here. So it mentions that the figure above shows a Ferris wheel. This is a Ferris wheel that you usually see in a fun fair, something like that. Okay, which has a diameter of 140 meter and takes 2 minutes to complete a revolution. So if you like to label it, then the diameter is 140 meters. So we don't usually need diameter. What we need is the radius. So the radius will be 70.0 meter. Okay, and it takes 2 minutes to complete a revolution. So means by if it's rotating, the this one is 2 minutes to complete a revolution. So there is one revolution every 2 minutes. Okay, so if you change it into angular velocity, this will be 1 revolution per 2 minutes. Okay, so if you want to convert it to a standard unit that we usually use, which is radian per second, we have to remove the revolution, we have to introduce the radian, and at the same time we need to eliminate the minute, then we have to change it into second. So 1 revolution is equivalent to 2 pi radian, 1 minute is equivalent to 60 seconds. So therefore we will get pi over 60 radian per second. Okay, so this is the amount of angle that has been covered by the Ferris wheel for every second. So every second that has passed, the Ferris wheel will be rotated by an angle of pi over 60 radian. Okay, a person of mass 50 kg takes a ride on the Ferris wheel. So we assume this is the person over here, and this person has a mass of 50 kg, and it's moving in a uniform circular motion. As the Ferris wheel rotates, the human here, the person over here, which sits on one of the basket in the Ferris wheel, will be tracing out a circular motion. Okay, if you focus on the motion of the person, you will see that it traces out something like a circular motion. Okay, so this is the motion of the person sitting on the one of the basket in the Ferris wheel, standing, I think. Okay, so calculate the angular velocity of the Ferris wheel. Oops, I think we accidentally found the answer already. So let's just write it clearly. Omega, initially we were given the value to be equals to 1 revolution for every 2 minutes. So we can convert the revolution. Okay, I think I'll just rewrite this, because we already discussed this. It's not worth spending too much time on it. Okay, 1 revolution is equivalent to 2 pi radian, and 1 minute is equivalent to 60 seconds. So if you do all the calculation, I believe you get pi over 60 radian per second. Okay, now after that they ask for the speed of the baskets of the Ferris wheel. Okay, the speed of the baskets, I presume they are looking for the linear speed right now, which is like how many meter does the basket travels for every second. Okay, like for every second, like, okay, let's say this is my basket, right? Okay, this is my basket. Every second that has passed, how much distance has my basket moved? Means like from here to here. Let's say for 1 second, travels from here to here. So they ask how much distance has been traveled by the Ferris wheel for every second that has passed. That's the idea of linear speed. If we talk about angular speed, that means how much angle has been covered by every 1 second that has passed. Look at the angle. When we talk about linear speed, we talk about the distance that has been traveled by the basket. So that is linear speed over here. Okay, I believe linear speed, you can relate it to the angular speed. We learned about this before in section 1, when we learned about parameters in circular motion. P is equals to r omega. You know that the radius of the circular path is 70 meter, and the angular velocity, we already obtained it just now to be pi over 60 radian per second. So if you calculate all these things, you should be able to get the answer of 7 pi over 6 radian per second. No, radian per second. What am I doing? Okay, this is linear speed. Linear speed, you talk about the distance traveled per second. So this one will be in meter per second. Okay, so feel free to also write it in terms of decimal places if you're worried that things expressed in pi is not really allowed. well, I think it's okay to leave it in pi, but if you are worried about it, feel free to change in decimal places. Okay, so next question, the acceleration of the baskets, the normal force exerted by the basket on the person and the normal force exerted by the basket on the person in different position when you are in basket A or when you're in basket B. Okay, let me be very clear. This is basket A, this is basket B. Okay, you might be worrying when you're confused which one is basket A, which one is basket B. So here is it clearly labeled. Okay, so to do all these questions, we'll be following the same steps as last time. Okay, first step we'll be drawing our free body diagram, sketching our free body diagram. Then after that we'll resolve our free body diagram. Then after that we'll analyze the x and y axis to see whether they are in equilibrium or not. Okay, x and y axis, check whether they are in equilibrium or not in equilibrium. Okay, why do we check whether they are in equilibrium or not equilibrium? Only we are able to know which equation to use. If it's in equilibrium, the forces are in balance, so the sum of fx or y should be equal to 0. And if it's not in equilibrium, then the sum of fx or y is not equal to 0, it's not balanced. It will be equals to mass times the centripetal acceleration, which you will need to label the direction of acceleration in the free body diagram. Okay, so we are going to follow these steps over here. Let's start by sketching the free body diagram. The acceleration of the baskets. This question is a bit... Okay. Oh, so the acceleration of the baskets, this one I think we are still able to do it without reference to the free body diagram. We have the linear speed over here, and we know that linear speed is directly related to the centripetal acceleration, using the centripetal acceleration equals to linear speed square over r. Okay, we can also use the centripetal acceleration equals to the radius times the angular speed square. Okay, both of these equations are equivalent to each other. It's just use the v is equals to r omega to transform from one form to another. So I'll just use I'll use this form then. Okay, why? Because the answer is in pi. Oh, this form is also in pi. Both are fine. Okay, I'll use this equation then. Okay, so if I use this equation, I'll sub in 7 pi over 6. That will be my linear speed. Square divided by the radius of the circular path, which is 70. Okay, so if I put it into my calculator and do all the calculation, I believe I'll get 0.192 meter per second square. Okay, so this is the centripetal acceleration, and this centripetal acceleration will be pointing towards the center of the circle at all times during the uniform circular motion. Okay, so that will be acceleration of the baskets. Next, you look at the normal force exerted by the baskets on the person in basket A or in basket B. So to do that, we probably need to sketch the free body diagram first to understand the situation more clearly. Okay, our free body diagram, do we need two different free body diagram? Let's see first. Okay, so this will be the situation for basket A, so let's label it as basket A. For basket A, we are sketching this free body diagram here, and this dot here is representing the person in the basket. Okay, we are drawing a free body diagram for the person, not the basket. Okay, so first we ask ourselves whether the person has mass or not. Yes, it has mass, therefore this person here will have weight. Okay, so this is the weight of the person. Next, we know that this person over here is not attached to any strings, ropes or cable. Okay, this one you might need to be a little bit careful, because I believe you all explicitly see that there's strings on the Ferris wheel. Okay, so the idea is like this. Okay, let's imagine that this black color object over here is the person. So over here, the person is in the basket, and the basket is connected to these strings, which is connected to the Ferris wheel. So right now you can see that the strings are in contact with the basket, but the strings here are not in contact with the person inside the basket. That's why the person inside the basket is not in direct contact with the string over here. Okay, you can call it cable or what. Okay, the person inside here is not in direct contact with the cable that is connected to the basket. Therefore, the tension is exerted on the basket but not exerted on the person over here. Okay, so we sketch a free body diagram, always focus on our object of interest, and our object of interest over here is the person over here. not the basket, not the cable, not the Ferris wheel. So if your focus or object of interest is the person, then the cable is not attached to the person, therefore tension is not exerted on the person. Instead, it's exerted on the basket. Okay, so for this situation, we will have no tension exerted on the person. Okay, the third question to ask is whether there's any force being explicitly mentioned in the question or in the diagram that is exerted on the person. In that case, I don't see anything being mentioned over here. So the fourth question will be to ask whether there's any surface in contact with the person or not. Well, this is the person over here, and we can see clearly that this person over here is in contact with the bottom of the basket over here. So because this person is in contact with the bottom of the basket over here, you should expect that the bottom of the basket here will be exerting a normal force on this person over here. Okay, normal force, the normal means perpendicular, means by the force should be in the direction that is perpendicular to the bottom of the basket. So the bottom of the basket is a horizontal surface, so that the normal will be pointing either up or down. To decide whether it's up or down, remember the keyword push. Normal force always push. Your bottom of your basket is pushing on the person over here. For the bottom of the basket to be pushing on the person, the direction must be up. Because for the basket to be exerting a force downward on the person, that will be called pulling already. The basket is pulling the person down. You want the basket to push. It's a normal force, it must be a push. Therefore, the bottom of the basket should be pushing upwards on the person inside the basket. That's why the normal force should be pointing upwards. Okay, so the next question to ask is whether this contact surface is it a rough surface or not. Well, this question is really irrelevant to the situation over here, because if it's indeed a rough surface, then the forces will be in the x-axis, then that is not really our concern over here. Our concern over here will be the forces that are in the axis that is intercepting with the center of the circular path. Okay, so this will be our free body diagram. Okay, so this is the free body diagram of the person in basket A. I should probably be clearer in my description. Should not say that it's basket A. Should say as person in basket A. Okay, so the weight is always constant, but this one and A, let's be more specific. This is the normal force when the basket is at position A, or we call it as basket A. Okay, for another free body diagram for the person which is at basket B, well, you know that the person will have mass. You go through the same process and you see that it's still the same free body diagram. There's no extra force, there's no friction, there's no additional friction or what in the discussion. It's just the same old normal force, just that this is a normal force when the person is in basket B. Okay, so if you are clear with the free body diagram already, actually we can start to look at step 2 already. So step 2 is to resolve the free body diagram, but we see that both of these forces are in the y-axis, so there's nothing to be resolved over here. We can proceed to the third step, in which we check whether the x and the y-axis are in equilibrium or not in equilibrium. Okay, for both of these free body diagram, we can see that the x-axis, there's no forces that we are interested with, so we can focus our analysis only on the y-axis only. And for the y-axis, we know that y-axis there should be an acceleration that is pointing towards the center of the circle, because that's how the object undergo uniform circular motion, right? You need acceleration to be pointing towards the center of the circle. Therefore, for this situation where the person is in basket A, the center of the circle is right under the basket. So therefore, you should expect the acceleration to be pointing downwards. So if I would like to label the direction of acceleration, the direction of acceleration should be downward. Okay, how about when the person is in basket B? When the person is in basket B, the center of the circular path, which is this point over here, will be above the basket B right now. So because this center is above the basket B, you should expect the centripetal acceleration to be pointing towards the center of the circular path. Therefore, the centripetal acceleration should be pointing upwards. Okay, so therefore our centripetal acceleration for the second free body diagram will be pointing upwards. Now that we are clear of the direction of the centripetal acceleration, we can proceed to analyze the situation using the equation that we have picked. Since both of these situations, they are not in equilibrium, we'll be using sum of F equals to mass times centripetal acceleration to analyze both of these situations. So let's start with question D first. So for question D, we are going to analyze the sum of Fy is equals to mass times acceleration, centripetal acceleration. Okay, so for this situation here, we are always going to take the force that is in the same direction as the centripetal acceleration to minus the force that is in the direction opposite the centripetal acceleration. So in that case, we'll be taking our weight to minus the normal force, and this unbalanced force, if you sum them up, will be equals to mass times centripetal acceleration. So this will be weight minus the normal force at basket A exerted by basket A on the person, okay, is equals to MA centripetal. Okay, so for this situation, we are asking for the normal force, so we shift normal force to one side, we bring all the other forces to the other side. Weight is just mg, so weight is just mg minus MAC. Okay, we have already determined the centripetal force to be 0.192. So bring along the value, don't round up yet, don't round it up, bring along the value, substitute inside, then I think we can get the answer. Okay, let's factorize out the mass first. Maybe mass g minus centripetal acceleration. The mass of the person is 50 kg. Our acceleration due to gravity is 9.81. Our centripetal acceleration is 0.192. So from this calculation, I believe we'll get an answer of 481 Newton. Okay, so this 481 Newton will be the force exerted by the basket A on the person over here. Because the person is standing inside the basket A over here, the bottom surface of the basket A will be exerting a normal force of 481 Newton on this person standing in basket A. Okay, how about basket B? For basket B, we are going to analyze it again using sum of Fy equals to ma centripetal acceleration. But this time, if you look at the free body diagram, you see that the normal force will have to be greater than the weight in order to have a centripetal acceleration pointing in the direction towards the center of the circular path. If your weight has a larger magnitude compared to the normal force, then the net force will be pointing downwards, then your centripetal acceleration will be pointing in the opposite direction. And that is not the case. We want our centripetal acceleration to be pointing towards the center of the circular path. So therefore, the normal force exerted by basket B on the person will be larger than the weight of the person itself. Okay, so in this case, you'll be taking the force in the same direction as the acceleration, which is NB, to minus out the force that is in the opposite direction to the centripetal acceleration, which is the weight. So this will be MB minus weight equals to MAC. Again, we leave NB on one side because that's what we want to find. You can see this is just mg plus mass times centripetal acceleration. Again, we can factorize out the mass, so this will be g plus centripetal acceleration. So this is just 50 kg, and this is just 9.81, plus the centripetal acceleration, which is 0.192 that we obtained from question C. So if you calculate everything, I believe you get an answer which is 500 Newton. Okay, so you can see that in the situation for basket B, your normal force will have to be greater than the situation when the person is in basket A. Why do you need greater normal force? Because you want your normal force to be greater than the weight of the person, so that the net force in the y-axis will be pointing upwards, which is towards the center of the circular path. Okay, that's when the basket is at the bottom of the Ferris wheel. You shift the basket to the top of the Ferris wheel. Now we want our net force, our centripetal force, to be pointing downwards. So the downward force will have to be greater than the upward force in order to have a net force pointing downwards. We are talking about basket A over here. So therefore, your weight will have to be greater than the normal force exerted by basket A on the person. That's why you can see that the normal force here is actually less than 550 times 9.81, because you want your NA to be less than the weight in order to have a net force pointing downwards. Okay, so this is how you understand the situation over here. And in fact, this value that you see over here will be the apparent weight. We also call it as apparent weight, or you can think of it as if the person is standing on a weighing scale. If a person is standing on a weighing scale in this Ferris wheel over here, this will be the reading of the weighing scale when the person is in basket A. You will see that the weighing scale weighs out 481 Newton. When the person is in basket B, you will see that the person weighs out 500 Newton. Okay, because the normal force exerted by the basket on the person will be equivalent to the apparent weight that the weighing scale will show when the person is standing on it. Okay, so I think that wraps up our discussion for this question on Ferris wheel. Thank you very much.